O. Łączysz to? Okay. Sorry for being late, but I went to grab some food and it took me more time than expected. Okay, welcome everyone to this presentation. The title is Wanna Race. It's about race conditions, something which is kind of a niche topic in web development, but I think it's kind of important, so I thought that it might be a good idea to make it. So about myself, I'm a senior software engineer at Intel right now. Previously I was a security engineer at Microsoft, and then I was working for BlaBlaCar and GOG.com, was over there. Basically I was a PHP developer for many years, and then I switched careers into security engineering, and right now I'm leading a project relating to machine learning and image processing. So I'm not doing PHP anymore, but you know, I'm still into high-level coding, into Java, into PHP and stuff like that, and I like to call myself as jack of all trades. So you know, kind of my specialty at conferences like that is to just present niche topics which are usually more of concern at a lower level for, you know, system programmers and so on, just to like kind of give a glimpse for people who are doing, say, web development and so. So I'm going to start with a question. So how many of you know what exactly is a race condition? Raise your hand. So that's 30%. Okay, that's good. Cool. So we're going to start first with what exactly a race condition is, right? So there is this joke, you know, where you're like knocking to the door and you're saying who's there, and you know it's Alex, and you're saying, oh hey Alex, come in, right? So the thing is that, you know, there is this interaction between two people, right? There's me on the other side, and then there is someone on the other side, and if you're too fast, you can like just start knocking and say who's there, it's Alex. You can just not wait for a response, and you know, it's going to be silence because he didn't hear me, right? So the race conditions is basically dependency on time. When you're having two things which are working at the same time, and in some way the timing is, you know, intervening, then basically you're having what it's calling a race condition. And then the race condition becomes a problem when one of those behaviors becomes undesired, right? Because, you know, sometimes we might not care about how timing affects the way the system works, but sometimes it's important because, you know, it's, for example, related to calculation, or I don't know, you're trying to count something, and you know, it's important that everything is precise. So what's important about race condition is that it needs a shared state. Okay, so basically when you're having a share nothing architecture, right? You share nothing, you do your work, it's completely separate, it's very cool. But when the work starts intervening each other, right? When, you know, one thread of work is depending on another one, then the problems, you know, start happening, because obviously it starts becoming timing sensitive. So I'm going to start by example. So this is ripped from Wikipedia. Basically, consider a very simple program with two threads, which is increasing an integer value, and here you can see an expected scenario, which is, you know, thread number 1, thread number 2, read value, increase value, write back, then read value, increase value, write back. Everything works fine, right? But there is a problem when those two, you know, because there is no synchronization in here, right? So it could happen that it works that way. You know, both threads read the value, they both increase, and they both write back. And the result is 1. So what happened here? So when you're accessing a memory location, you are making an assumption, okay? So when you're reading that value, 0 in this case, you're making an assumption this is going to stay that way. And if you're not doing something about holding that assumption, the system is not going to do it for you, right? So it might happen that this assumption is broken, right? So in this case, you can see that, you know, the assumption is here, and then the assumption is broken because, you know, something else read that value, and basically at this moment, what this thread assumes, what this thread assumes to be true is not true anymore because the other one increased the value, right? So that's basically what we're calling a race condition. And then I want to talk a bit about PHP. I want to talk about the execution lifecycle in PHP. So, you know, I wanted to delve a bit deeper into how PHP historically was, you know, processing requests, because that's the important part here. And I've read somewhere that PHP insists on dying fast. Okay, so PHP was designed by itself to die fast. You know, like PHP at its very beginning was basically a language to parse HTML, right? So it was a scripting language where basically it was like processing some HTML dynamically. So it made sense at the time to design it as a language, you know, where it starts running, something changes, you know, everything is generated, it's written, it dies. Cool. But of course, things changed. Right now we're using PHP for enterprise applications which are serving requests continuously, and this poses, well, some problems. So everyone who deployed PHP applications is probably familiar with at least one of those stacks. So basically, you know, back in the days we had AppH2 with prefork npm and mode PHP 5. So that was, you know, like a classic deployment. Then we had a very similar stack, but with work on npm, and then eventually everything migrated to Nginx and fast CGI implementation. For example, PHP FPM. So basically, you know, Nginx and PHP FPM are right now like the most common setups for deployment for PHP applications. So the question is basically, what do they have in common? So I've digged a bit into the code, and this is the code from mode PHP 5 for AppH, right? This is C code. So the important part here is this function, Zen execute scripts, and I want to show you the parameter which is sent here, and look at what was sent. Its file name. So basically it says execute a script at this file name. And if you look at PHP FPM, basically there's this function PHP execute script, which in turn also uses this send execute scripts, right? So basically in current deployments and in past deployments of PHP, there was never a notion of shared state. Like when you're having a Java application or a C++ application for that matter, basically this application lives. There's a process that's living and it's continuously serving requests. Meanwhile, in PHP, basically each request was asking to parse a script at a given location and run it. And the problem is that means that there was like no shared state, right? So basically for each request there was like a new state run, and there was basically share nothing, right? So everyone who codes in PHP knows that basically, you know, every execution context is being like killed off after each request. So there is, for example, no way to share data easily between requests in PHP, right? So in terms of race condition, that should be good, right? Like, you know, there is nothing shared, so what's the problem? Well, the problem is we're not living in a vacuum, right? PHP runs on something. PHP runs on a Linux system, which runs on CPU and RAM. And then there is web server, which is AppH or Nginx. And then there is, most importantly, database. There's MySQL, there's PostgreSQL, there's caches. So basically, you know, like PHP won't raise PHP, but it can raise PHP through other services, right? Because we are accessing data from other sources. So I'm going to go by a simple example to explain this problem. So I wrote this very simple function. Basically, there is a query to a database, which selects discounted products left from a table called products, and basically it checks if it's 0, and basically it gives a discounted product, otherwise it gives a full price product. A very simple thing. So again, there's an assumption made at this moment where this is being queried and this is being checked. that this is still true. But when we read that value here, this assumption won't hold. We have absolutely no guarantee this is true. For all that matters, this could change to anything because anyone else could make a query which would update this field. So that's a problem. Well, at least for some scenarios. Like, for example, I remember one situation. I was working for a company which was selling video games, which I'm not going to call, but you probably know it. And basically, we're like giving out games, and there was like a cache variable, and obviously we tried to like go one by one with each game given, and of course at that moment I didn't code it properly. So because of that race, the number was a bit off. It was off by a few products, right? So that was a problem because where are we going to get those products from? So what can be done? So the way concurrency is solved is by a process called locking. So basically a lock means that you are acquiring a resource and that no one else can access it at that moment. So basically, this is the example we had earlier, but with locks. So basically you can see that the lock is being acquired and then the operation is being made. And you can see that the other thread tries to acquire the lock but fails because it was acquired before by someone else. It has to wait until it's being released. When it's released, you can safely acquire the lock, okay? So basically, this is like a primitive to ensure that you are the only one who are working on specific data. And that way you can ensure that, no one else is going to modify it at this moment. And then the other thing is a concept called atomicity. So basically, when we're talking about a set of operations, right? So when we are having those read value, increase value, write back example, you could say that for the high level view, it's like increased by 1, okay? So it's like visible as one indivisible operation, right? That's what atomicity is about. And when we go back to this, when we're going to implement it like this, with logs and all, we're going to make sure it's thread safe. For outside code, this operation is going to be atomic, right? So, the code which is consuming this can be sure that everything is working fine. Again, what we can do about this problem? As I said, it's about locking and atomicity. So I'm going to say a bit about how it works in MySQL because I thought that's like the most common problem. And MySQL provides constructs for explicit locking, which are not used very often, which is a shame. So basically, what happens is you're starting a transaction here, and then you are basically asking for what we call a shared lock. So now I'm going to stop and explain what a shared lock is. So when we're talking about locks, there's a lock which is called a shared exclusive lock. So how it works is basically you can acquire two types of locks. One is a shared lock and one is an exclusive lock. You take a shared lock if you want to just read the value, and you take an exclusive lock if you want to write a value. And why is that important? Is because the rule is as follows. When you acquire a shared lock, someone else can't take a shared lock but cannot take an exclusive lock. So basically when you are reading, others can read but others can't write, okay? And then when you're talking an exclusive lock, no one can either take a shared lock and an exclusive lock. So basically, when you are writing, you are saying, I don't want anyone to read and I don't want anyone to write. And the reason this is done is because basically concurrent reads are not a problem, right? Because they are not mutating the state. So that's why it works this way. So basically, to take a shared lock in MySQL, you have to annotate your query with a for share here. At this moment, a read lock is being taken, and you can be sure that no one modifies this value, and you can process it in any way you want. And basically, when you're done, you are committing the transaction, and basically the lock is freed. Similarly, if you want to write a value, the very similar construct exists. It's called for update. When you query it that way, an exclusive lock is being taken, and you can be sure that no one reads or writes this value, and you can update it safely that you're sure that no one else is going to modify it. And now about atomicity, right? So as I said, atomicity, I consider atomicity to be an abstraction. So basically, when you're saying something as atomic, you are basically given a guarantee that something is thread safe, that it's one indivisible operation and you don't have to worry about it, that it's going to, be broken somehow. And a lot of tools we're using actually offer you ways to preserve this atomicity. So basically, this is the very same example. It was just rewritten to use atomicity primitives in MySQL. So you can see that basically what I did here is I'm calling an update immediately, and I'm putting the comparison into the query. So, when I'm executing this query, basically, the database kind of ensures me that this is being done as one atomic operation, okay? Because each query is considered atomic operation in the database, and basically that way I don't have to do any synchronization by myself because database is doing it for me. So I can just do this query and everything works fine. Okay, I'm not sure how much time passed. So basically, summary conclusions. So PHP by itself is designed to have a share nothing, which is very useful because you don't have to share nothing, so there are no problems which can happen in other languages. But several PHP requests can raise because of what I said about other services and the data being shared. So the important point to understand about concurrency is that ensuring safe concurrency is expensive from performance point of view, because when you are doing that, basically you are saying others have to wait for me, and we don't want others to have to wait for me because we are delaying their work. So basically the performance of the system is overall lower, and that means that basically you should use synchronization primitives and atomicity and locking when necessary. So that basically means that you have to make sure that you made everything possible to make your architecture as share nothing as possible. Okay, because it's always going to be better. And then if you cannot do that, which can happen, then you have to design carefully, because race conditions are very subtle bugs. They're depending on very non-deterministic behavior on the system, because it's depending on timing, and many different factors can change the timing. So basically, things which happen in production won't happen in debug. Debug builds will work, but production won't, or the other way around, or it will just happen every other time. So they're very hard to reproduce, very tough to debug. So the overall consensus is to make sure that you design carefully, because the cost of fixing those bugs is very, very high. I believe one of the highest in any other bug class. And yeah, as I said, when it comes to concurrency, I believe that if you don't have to do that, just use the atomicity provided by your system. So if you're using MySQL, make sure you're writing queries which are as atomic as possible. Don't do the pull operation push by update. Try to do everything in the query, right? Try to push the responsibility to the database, because it guarantees you those things, and basically you don't have to worry about it, and that's a great thing. That's what the abstraction should be about. And if you can't do that, then basically you have to design your locking carefully by basically what I showed you before. Yeah, I've kind of tried to rush because I had 30 slides in 30 minutes, so I'm not sure how much time we have for questions. 9 minutes. Okay, so we have 9 minutes for questions, so you guys are free to ask right now. I don't have anything to give you for questions, but accept answers. Yeah, go on. Do you want a microphone? Do you want a microphone? I'm going to give you a microphone.
Hey, thank you for Hey, thank you for the presentation. I have a question about deadlocks. Do you face them often? And if so, how you manage to share, like, to synchronize a shared state between separate threads?
Okay, it works. Okay, so first, because I think it would be fair to first explain what the deadlock is, because I didn't include it, and you're actually right that it's an important thing to do. So the deadlock is basically a situation where there are two threads which acquire locks, for example, in the reverse order, and they start waiting for themselves indefinitely, right? So basically, there is, for example, I don't know, you lock thread 1 locks lock A and then lock B, and basically there's another thread which tries to lock in the reverse order, and then it starts waiting, and it will never exit because they start waiting for each other's locks, right? So it doesn't really make sense. To answer your question, when it comes to PHP, I didn't encounter it much, and the reason is because at the time I was writing PHP, I really sucked at concurrency. Okay, so I was really bad at it. So I didn't fix it because I didn't know how. If I were to write it right now, I would probably encounter this problem because it will probably happen. But what is important about this question is that the colleague here makes a good point that we should be careful about designing or locking architecture, and especially avoiding acquiring multiple locks, because it can be dangerous. Because when resources start waiting for each other, it can happen that basically it goes into deadlock and everything stops working. So it can be a problem. Okay. Any other questions? You sure?
Really sure?
Really sure?
Okay, cool.
Okay, cool. Okay, thank you very much then. Yeah, so if you guys have any questions, just, I'm going to be here for a few minutes, and then you can catch me on Twitter, which is Alex Fortune with with 0 instead of O, and then there's my mail, so you can just write me an email. Or some of you guys, if you are on PHPers group on Facebook, you can just write me here, because I'm writing there pretty often. Okay, thank you very much for your time then.